Hello, class. So today, what I want us to do is kind of get into thinking about what an antiderivative is and incorporate that with what we call indefinite integrals. Okay. So first things first, notation is important. All right. How you represent things is important. That's how it makes integration a whole lot easier if you represent things the way they're supposed to be represented. Okay. So let's look at what I have here. It says that if f of x, so f of x is what we are calling the derivative of the function. It's not f prime. If it is f prime, that's fine. But when we are in the world of integration, your f of x represents the derivative of a function. Then we're going to use big capital F of x to represent what the antiderivative of f of x is going to be. Right? So when you see big F, that's the original function. When you see little f, it represents the derivative. All right. So the way we write this mathematically is we are going to say, let me get rid of this first. Now let's discuss what's going on here. So what this is saying is that this elongated S that you see here, this body here, is called the integral sign. All right. And then f of x dx, anything that is inside of the integrand is what we're going to call the integral sign. Anything that is inside of the integral sign is what we're going to call the integrand. All right, so two words that you need to know, the integral sign and then the integrand. So all this is saying is the integral sign is indicating to us that you want to find the antiderivative of f of x. And when you find it, that is what we are calling big F of x. All right. Then we tag along a plus c to show that every derivative, if you have a constant, when you take its derivative, it goes to zero. So when I have my f of x, my big F of x, I do not know if it has a constant or not. So because of that, we're always going to attach a plus c, which we call the constant of integration, so that we've accounted for any situation that this function might have. If it had a constant term to it, it would take care of that for us. So this is what we call this process that we just went through, finding the antiderivative using the symbol notation, the integral sign and all that is what we're calling the indefinite integral. All right. Indefinite integral. And the cool thing about indefinite integral is that it returns to you a function. All right. When you integrate, if you do the indefinite integral or you find the antiderivative, you end up getting a function back. Very soon, we'll also learn what we call the definite integral. All right. And for that, it's very similar to an indefinite integral, but it's got two special things. It's got an upper bound and it's got a lower bound. All right. And the outcome is always a number, it's always a value. So unlike indefinite integral, where the outcome was a function, when you work with a definite integral, you end up getting a value. And we'll look into more details very soon how we manipulate definite integrals. All right. But for now, we want to focus on antiderivatives, or what we call reverse differentiation, if that's another way you want to see it. But That's what we have now. We've learned so much in derivatives that now is the time for us to reverse every single integral that you learned. So the very first few ones we're going to do, you learn how to do the power rule. So we're going to learn how to undo the power rule. You learn how to do e to the x. We're going to learn how to undo e to the x. We learned about your trig derivatives. We're going to learn how to undo those. And then things start get complicated, so we start using different techniques to help us to return us back to what the original function was. All right, so I have this table over here, and I want us to look at it really closely and see if you recognize what's going on here. So on the first column, I have f of x, and remember, f of x represents a derivative. All right, a particular solution is a solution that describes just one family of what the original function is. So one of them could be when c is equal to 0, right? And when we talk about the general solution, that's where we are considering all the families of solutions that could possibly come out when you find the antiderivative of what f is. Okay, so that's what's describing the three columns that I have over here. So if you think about a constant, so b is a constant. If you think about a function that you took its derivative and you end up with a constant, then you can clearly see that that function had to be what? Bx. Because when you take the derivative of bx, you get b. And if you take a general case, that's going to be bx plus c. Well, if you have a number, if you look at the second one, so this is 1, 2, 3, 4, 5. That's e to the x. 6. All right, let's look at those few ones, and I'll leave the rest for you to look at it and absorb it a little bit. So if you look at number 2, it says c times f of x. So cast your mind back and think, okay, if I had a function and I multiply with a coefficient, then if I want to return myself back, since big f of x represents the original function, then that had to be c times big f of x, because now when you take the derivative of c times big f of x, you end up getting c times little f of x. All right, x to the n, this is very powerful. This is what we call the power rule of integration. I'm looking at number 3 right now. And when you look at that, you can clearly see that what we do is you increase the power by 1 and divide by the new power. So it is indeed a reverse of what you did in derivatives. In derivatives, you did what? You multiplied by the power and then you subtracted by 1. So if you're going to reverse, you'd have to add 1 to the power and then divide by the new power. All right. And then you also looked at 1 over x. What is the antiderivative of 1 over x? Can you think of a function whose derivative will end you back at 1 over x? And that was ln x, absolute value of x. All right. Hopefully the video you watched the day before today explained better why we need to use the absolute value. All right. And then e to the x is still e to the x, but if it's e to the nx, then you can clearly see that its antiderivative has to be e to the nx all over what? All over n. And then we enter into the world of trig. So your goal here is, can you recognize all these trig derivatives and be able to say, okay, if I'm looking at sine x as the derivative, then where did it come from? Well, it came from negative cosine, because the derivative of cosine is what? Is negative sine x, which is positive sine x. So you reverse engineer all your derivatives, your trig derivatives, and then you can also look at your arc length. So your arc length functions, your trig inverse functions, you can clearly see that if you have 1 over 1 plus x squared, where did it come from? It came from arctangent. All right. So the best way to do this is to go through some examples. So let's try and see if we can go through a couple of these examples and see if it makes sense to you. Okay. So I'm always going to apply a technique when I'm integrating, right? If you do a problem without realizing, okay, I just did this without any technique, you're on the wrong track. Okay. So when I look at the first question, it says, find the antiderivative of x squared. That's what this whole mathematical expression is saying. Also, it is important to note that the dx means that you're taking respect to x. Later on, we'll look at it from a different perspective, but this is telling you that you are integrating a function of x with respect to x. Okay, so you cannot ignore that dx and I'm just going to write the integral of x squared. No, everything comes together to mean something. All right. So back to the problem that we're trying to solve here. So if I'm trying to solve this, I can clearly see that I see x to the n. It looks like number 3. So I can apply the power rule of integration, which says I'm going to increase the power by 1 and divide by the new power. So this becomes x cubed over 3 plus c. Don't forget the c, right? Start with the plus c so that it doesn't become a problem for you by forgetting to put the plus c because it's very important, all right? Let's look at, and then this is what we're calling that f of x, big f of x is equal to x cubed over 3 plus c. Okay, let's look at the next question. So the next question, it feels like I could utilize the power rule of integration, but things are not in their right way. So most of the time, what you'd have to do is you need to clean up the expression to arrive at a place where you are comfortable seeing that you recognize a technique to apply that problem. Okay, so here I'm going to rewrite this as the integral of x to the 1/2 plus x times x to the 1/3 dx. I'm almost there. By applying my rules of exponents, I get that to the 1/2 plus that to 1, so I get x to the 4/3 dx. At this point, I'm feeling a little bit comfortable because I recognize x to the n. I can apply the power rule of exponents or the power rule of integration to this problem set here. So this says I'm going to get x to the 1/2 plus 1 divided by 1/2 plus 1 plus x to the 4/3 plus 1 all over 4/3 plus 1 plus c. All right, don't forget to put the plus c. All right, so if I clean up everything, I'm getting x cubed over 2 divided by 3 over 2 plus x to the 7 over 3 divided by 7 over 3 plus c. And then if I clean up the fractions that I have, I get 2 over 3 x to the 3 halves plus 7 over 3 x to the, no, it's supposed to be 3 over 7 x to the 7/3 plus 1. Let's see. Okay, and this is what we're calling big F of Y, big F of X. All right. Now let's look at the next question. All right, and see if you can pick up a pattern. All right, so I have x plus 2 all squared plus 1 over x squared plus 1 dx. I want to integrate or find the antiderivative of this expression here. Well, right from the word go, you don't recognize any derivative that gives you x plus 2 squared. But algebraically, you can break this down. So if you break that expression down, you end up getting x squared plus 4x plus 4 plus 1 over x squared plus 1 dx. At this moment, you can clearly see that you recognize this is x squared. It's a power rule of integration. You see 4x, you can use power rule of integration. You see 4, you can use a power rule of integration. And then you see 1 over x squared plus 1. At this moment, you should be like, ooh, whose derivative is that? Right? And I bet you got it right. It is supposed to be what? Arctangent. So by inspecting each term, you are able to discover that you have a way to find the antiderivatives. All right, so let's quickly find this. So this will become x cubed over 3 plus 4x squared over 2 plus 4x plus arctangent x plus c. Always don't forget your plus c. And then let's clean things up so that we now have x cubed over 3 plus 2x squared plus 4x plus tangent inverse x plus c. Okay. It's a little lag time going on. Okay. Alrighty. Okay. Let's look at the next question. So I have a little 3D question here. And again, when you look at the expression given, right, x plus x squared over x cubed, it feels like, well, there is nothing in these rules that I just listed up here that you can use, but you can use your algebra skills to simplify expressions. All right, you can use your algebra skills to simplify some expressions. So, all right, so let's return back to what we're trying to do here. I have to go close again. All right, so for me to solve this expression here, I need to break things apart so that I can return myself to a place of comfortability. All right, so by algebra, you can see that you can split this up as that cube plus x squared over x cubed dx, which cleans up nicely to give you 1 over x squared plus 1 over x dx. Well, to solve the first term, really I have no choice but to bring everything back up to the numerator, so that's x to the negative 2. But then I don't have to do anything with the 1 over x because I recognize a derivative that returns me back to what? That gives me 1 over x. So I'm going to leave that one in that form. And then I'm going to try and apply the power rule of integration over here, which gives me x negative 2 plus 1 divided by negative 2 plus 1 plus ln absolute value of x plus c. So this cleans up nicely to give me x to the negative 1 minus plus ln absolute values of x plus c, which eventually becomes 1 over negative 1 over x plus ln x plus c. All right. At this point, I hope that you are catching on some new tricks, right? Because if we find the original function, to know that you're certainly right, you can always take the derivative and see if you return yourself back to what was given, right? Because the expression in here represents a derivative. So if you take the derivative of this expression here, will that be equal to what I have in that circle? All right, and that's the beauty about integration, that you can always check your work. All right, let's look at number 4. So number 4 says that you have e to the x plus cosine x. So when you find the antiderivative of e to the x, it's itself. And can you come up with a derivative, a trig derivative, whose outcome is cosine x? So the derivative of sine is what cosine is. So this has to be sine x. And don't forget your plus c. Let's look at the next one. So the next one is e to the 2x plus secant squared plus 1 over x. Clearly, I can see that I can find this. This is plus what? Plus tangent x. And then that is ln absolute value of x plus c. The question is, how do I find the antiderivative of that? E to the 2x. So remember that the derivative of e to the x is itself. So with e to the 2x, that means that you might have had a constant of 1/2 e to the what? 2x. Now when I take the derivative, I can clearly see that I have the same thing. Okay. Now let's see how this is applied to a problem set. So here I have a derivative that is given to me 2x plus 5. And it wants me to find big F of x. When they give me this condition here, big F of x at 1 is equal to 2. Right? So I want to return myself to the original function. I have to do an antiderivative. So I'm going to do the antiderivative of 2x plus 5 dx. Notice I didn't drop my dx because it's part of the setup. And then now I can see that I can find the antiderivative of 2x is just 2x squared over 2 plus what? 5x plus c. All right. At this point, this is supposed to be equal to big F of x. That's the original function. Well, they give me a condition that at 1, the y value is 2. So I can do big F of 1 is equal to what? 2, 1 over 2 plus 5 times 1 plus c, and that outcome is 2. So I end up getting 6 plus c is equal to 2. C is -4. So that original function was x squared plus 5x minus 4. And then finally, let's look at the last question. So the last question says that you have an acceleration of a particle and it's given to us as a of t is equal to t squared. Find the position function x of t if v of 0 is 2 and x of 0 is 10. So here they're giving me acceleration and they want me to find position. So I'm going backwards twice because when I take the antiderivative of acceleration, I get velocity. When I take the antiderivative of velocity, I get what? I get position. So I'm going to integrate a of t dt, and that gives me t squared dt, which will give me what? T cubed over 3 plus c, which represents v of t. Now they give me that initial condition because they want me to resolve that c. So at v naught or v0, I get that's supposed to be equal to 2, implies that I have 0 over 0 cubed over 3 plus c is equal to 2. C is 2. So v of t is equal to t cubed over 3 plus 2. All right. Now I have the velocity function. Well, the question is, how do I find the position function? So to get the position function, I need to integrate the velocity function with respect to t, and that is going to give me the integral of t cubed over 3 plus 2 dt, which will give me t to the 4th over 3 times 4 plus 2t plus c, and that gives me x of t. So I end up with t to the 4th over 12 plus 2t plus c is what x of t is. But they give me again enough condition. They tell me when the position is at x at t equal to 0, x position was at what, 10. So I can set this up as 10 is equal to 0 over 12 plus 0 times 2 plus c is equal to 10. And I can clearly see that c is what? C is 10. So what is x of t? X of t is t to the 4th over 12 plus 2t plus t. Okay, so hopefully this gives you an idea of what we're trying to do. All the basic integration techniques that you learned, we're going to try and undo all of them. But for now, the basic ones that we're able to undo are your power rule of what differentiation, which we now know we can use the power rule of integration to figure it out. And we know how to undo all our trig expressions and our natural log and our e to the x. We know how to undo all of them and also use to apply to simple basic application problems. All right. So see you in the next video. Bye.